Now I want to look at what are called differentials, and as the name implies, it's closely related to a derivative. So here's the definition of what a differential is. It's this thing right here. dy is f prime dx. So that's looks a whole lot like if I take the dy dx, that's equivalent to saying f prime. It looks like I'm just taking this and splitting it up, putting it over here. And if that helps you remember it, that's good. But that you really can't do. This is just notation when we do this. But here's notation as well, which looks like it makes sense to say exactly this. So what we're interpreting here is we call this the differential of some function f. And so all we are just splitting up. We're just taking f prime, and then we have this notation of dy and dx. The dx and dy are the actual differentials, and the dy, we can use it to approximate the actual change of our function. So let's draw a picture. Suppose I have some function coming through here, and I have this tangent line approximation to it at this point. And so this is happening at some x, and then we're going to step over here a little bit away from x, some distance delta x. Well, we're going to use delta x to be our differential x. Those turn out to be one and the same. But so my actual function is here, and this is my delta x, and this would be delta y. So like I said, delta x and dx, we consider those the same. But if I were using the approximation with my my tangent line approximation, this would be what I'd be approximating the function's value to be. The actual function value would be f of x plus delta x minus f of x. That's what this distance is. That's how much it's changed. That's the change in y. But this would be my approximation. You can see I'm missing it, and I'm in my picture it looks like I'm missing it by a lot. But if we zoomed way in, this might be 1/100th or whatever. But this distance that my linearization, my tangent line is missing it by, that's what we're going to call dy, and we're going to say that dy is approximately delta y. That's our approximation. So if you're following the tangent line and using that to approximate, you get a dy. And tangent lines are used to approximate things just because they're easy to evaluate, and maybe you don't have the actual function, and so you have to have some sort of scheme for approximating. So that's our idea, is that we're going to use this this dy, and this is coming from my tangent line approximation. And so here's a simple example. It says find the differential for this function, or the differentials might be a better way to say it, but usually we just call it the differential. Here's the definition of the differential. And for this problem, I get 1/2 square root of x dx. That's my differentials. What is the value of the differential if dx is 0.1 when x is 1? Okay, well that's pretty easy. You just plug in the value of dy is 1/2 times the square root of 1 times 0.1. And if you work that out, you get 1/10 and 1/2, that's 1/20th, which is 0.05. Not too exciting, but let's look at a different way of explaining what's going on. So suppose I'm using this function to build something, or I'm using it for some physical application. And what the differentials allow me to approximate it, what this is saying is if I miss my actual value, so I'm trying to plug a value in, I'm trying to plug in 1, and for some reason the value that I'm plugging in, so if it's a physical application, maybe I'm building something, and this gives me an output of whatever I'm building, it gives me its area, or it gives me the volume of it, or how much paint it's going to take to paint it, or whatever. Somebody worked out a formula saying, okay, when you want to build this thing, this is what it's going to take to paint the object. Well, suppose I built this thing, but I'm off, my dimensions are off by 1/10. Whenever I'm supposed to be at 1, maybe I'm at 1.1, or maybe I'm at 0.9. Well, what the differential gives me is an estimate of how far off this output's going to be. I could miss by 0.05 from this formula. This formula's outputs could miss by this much. So if I have this much error in my input, this is saying this is how much error I could have in my output. So it gives you a way to sort of get a handle on how much input error gives you as an output error when you pass it through the formula. And so that does give us this notion of relative error. So remember, delta E, if we have some function, this is the our definition. Dx and delta x are the same thing for us. So this is the actual difference for some function. The relative error is, well, so if I give you that the error could be 0.05, that doesn't mean a whole lot. If I'm measuring, the size of a lake, a 0.05 error is pretty good. But if I'm measuring the size of, something on the scale of a cell, this might be a big error. So we do want to come up with a relative error, meaning, relatively speaking, to the actual value I'm supposed to get, how much is the error? So you take the actual error divided by the actual value. Well, we don't have the actual error, so typically what we use here is we use DE, the approximation that we came up with, and divide it. So in this problem, it's not very exciting because my relative error turns out to be 0.05. The actual value would be the square root of 1 is what I was supposed to get. And so my relative error turns out to be 0.05. And sometimes as a percentage error, it makes more sense to someone when they read it. So that's a 5% error. So a small error in the input does give me a 5% error in the output of this thing. And the question would be, is that acceptable or not? Who knows? I mean, if you're building a space shuttle, that might not be acceptable. If it's going to, you have some sort of fire retardant that you're spraying on there and you miss it by 5%, you might be in trouble. So let's look at an example that's sort of realistic. When you go get your any kind of medical test, usually they take your pulse, and so what they do is they want to know heartbeats per minute, and they take your pulse for about 10-15 seconds, and let's say they do it for 15 seconds. Well, that gives you how many they counted in those 15 seconds, and then they multiply it by 4 to say, well, that's your heart rate. Well, so there's obvious error there, because while they're holding onto your wrist, taking your pulse, it may be that they're watching, they're looking at a clock for 15 seconds, and just when they pull away, there was going to be another beat. So technically, maybe they counted that you had 15 heartbeats, but maybe it was 15.75 because you were about to have another heartbeat. So you can see there's obvious error built in, measurement error. And so the idea is we've got this formula that your heart rate, based on the number of heartbeats that they count, let's say they're doing the 15-second interval, they'll take whatever they count and then multiply by 4, and that'll say that's your heart rate. But I want to know, how much could they miss that by? So the error on the input is they could miss it by probably 1 full heartbeat, you would think, because it could have just been about to be a heartbeat when they let go. So that's essentially 1 heartbeat missed. So I would say the most they would miss by would be up to 1 heartbeat while they're counting, assuming they don't get distracted and count wrong. So if they're counting right, watching the clock right, they might miss it by up to 1 heartbeat. Well, then what's the corresponding error in your actual heart rate? Well, that's this. We use DH as the estimate on the error in your heart rate. Well, that's just going to be 4 dB. I'm using differentials here. And so that says that with up to 1 heartbeat error in the input, you could have up to a 4 heartbeat error in the output when I plug in the 1. Now, is that important? It depends on, how healthy the person is or what they're testing you for. If they're testing you for having a slow heart rate, that might be important to know if your heart rate's slow or fast heart rate or whatever. Or if the heart rate's very important in the process, they probably need to be a little more accurate. And so what's the relative error? Well, let's see. Relative error in this case is the amount of error that I came up with over what the actual value is supposed to be. Well, so let's say I need a particular B. So what's the relative error when B, let's say they counted 15 heartbeats while they were counting. So I'd have supposed to have a heart rate of 60, because from this formula I should come up with 60. Well, 4 out of 60 is 1/15, and if you use a calculator, that's about 0.07, 0.666. So a relative error of 0.07 or 7% error. And again, the question is that acceptable? And it depends on what they're testing you for. It might be just for every day someone comes in, they just want to make sure they're going to donate blood and they don't want to have a high heart rate. Well, 7% might not be a big deal. But like I said, if it's condition that heart rate is very important to know, then you might want to be a little more accurate by actually counting it for 60 seconds or 30 seconds or using some special monitor to help figure that out.